Turning Plastic into Light. How German scientists reimagined polyamides for LEDs. Polyamides, the synthetic polymers best known for making durable nylon fabrics and high-performance engineering plastics, have traditionally been valued for their strength and heat resistance rather than their optical properties. However, a research team at Justus Liebig University in Germany has successfully re-engineered these materials to emit broad-spectrum white light when exposed to near-infrared lasers. This breakthrough suggests that polyamides could play a pivotal role in the next generation of optical devices and light-emitting diodes, LEDs, offering a simpler, more stable alternative to current technologies. From flexible chains to rigid diamonds, to understand the significance of this development, it is helpful to look at the history of polyamides. Introduced commercially by DuPont in the late 1930s, nylon revolutionized textiles and later found critical applications in military gear during World War II. Its successor, Kevlar, developed in 1965, remains the gold standard for body armor. Today, polyamides are ubiquitous in automotive parts, electronics, and packaging. The structural integrity of these materials relies on hydrogen bonds that link neighboring molecular chains. However, conventional polyamides are flexible and do not naturally generate light. To overcome this limitation, Professor Peter Schreiner and his team sought to redesign the polymer's molecular architecture. Instead of using traditional flexible building blocks, the researchers incorporated diamanting, a rigid, three-dimensional molecule naturally found in crude oil that resembles a miniature diamond. Replacing their flexible building blocks with rigid diamanting units transforms traditional structural polymers into materials with novel and advantageous light-emitting capabilities. Explains co-author Saravanan Gaurasankar. A simpler path to white light. The resulting diamanting-based polyamides emit white light under near-infrared laser irradiation, without the need for dyes, dopants, or inorganic salts. These additives are currently standard in the industry to tune light generation, but often introduce significant drawbacks. Reduced stability. Additives can degrade over time. Complex processing. They complicate manufacturing workflows. Higher costs. Additional materials increase production expenses. By eliminating these additives, the new material offers a streamlined approach. Our approach simplifies the material system, enhances stability, and is potentially more dependable and scalable for practical applications, says Schreiner. Heat resistance. A critical advantage beyond light emission, the new polyamides exhibit exceptional thermal stability. While traditional nylon 6 and nylon 66 decompose near 400 degrees C, the diamanting-based variants remain intact well above this temperature. This property is crucial for two main reasons. Operational durability. High-powered lasers generate substantial heat. If a material cannot withstand this thermal load, it may degrade or lose its functionality during operation. Manufacturing viability. The fabrication of light-emitting devices often involves harsh, high-temperature conditions. A heat-resistant material ensures that structural and optical properties remain intact throughout the production process. Surface structure dictates performance. The efficiency of light emission in these new polyamides is not just a matter of chemical composition. It is also dependent on physical structure. The way polymer chains are organized at the surface determines how effectively the material interacts with laser energy. Rough or nanocrystalline surfaces enable efficient conversion of laser energy into broad-spectrum white light. Smooth surfaces result in highly flexible chains that lack the ordered arrangement necessary for efficient interaction with the laser field. Looking toward commercialization, while the scientific principles are established, moving from the laboratory to the marketplace requires addressing several hurdles. The researchers are currently exploring lithography, a technique used to create precise, microscopic structures on surfaces to design individual diamanting structures. Their goal is to create larger polyamide architectures that can be integrated into functional, high-performance thin films. Schreiner outlines three primary challenges for future development: enhancing emission efficiency, integrating the material into existing device architectures, developing scalable manufacturing processes. Conclusion: this research demonstrates that by altering the molecular rigidity of common polymers, scientists can unlock entirely new optical properties without relying on complex additives. If the challenges of efficiency and scalability are met, diamantine-based polyamides could offer a robust, heat-resistant foundation for future lighting and optical technologies.